this short. Yes, let's just jump right into it. So in 2021, University of Zurich had, in collaboration with ESA and NASA JPL, a European-wide airborne campaign. Here we see this little aircraft which came over the Atlantic to us to take images, hyperspectral images with AVIRIS NG throughout Europe. And the main objectives of the project I'm presenting here today was to select a multi-sensor data set where we have matchups of AVIRIS NG, PRISMA space-based and DESIS space-based hyperspectral imaging sensors, and the ASD, which we used as ground comparison points to do a data quality analysis. Also, what we wanted to achieve is a consistent atmospheric processing that did not quite work out because it is more complicated and more complex than expected to reprocess AVIRIS and G data. So this means we have similar but not equal processings. And then I think there is someone not mute. Mind. I hope you can still hear me. In the end, we did a cross-validation and uncertainty assessment of the data sets we have. For this project, we selected 6 regions throughout Europe. You see them here in red. These were positions or areas of interest where the sensors were matching up within ±1 day. And in this project, we were focusing especially on Camarena down here in Spain, where we had the images at the exact same day, but spread throughout the day. So this is important because we will see some effects of this afterwards. So image reprocessing, as I said, we tried to do AdCore with AVIRIS NG. That did not work, so we're still on ISOFIT. With PRISMA and DESIS, however, it was possible to process the data with AdCore, and here with PACO, which is a Python version of AdCore. And then in the end, to really have a perfect matchup also geographically, we used AROSIX to, like in a rubber sheet approach, move those images and base them on the Sentinel-2 GRI image. And then in the end, we had this MSDS, a multi-scale data set. Why is this entire thing important? Well, for CHIME, you have to develop new algorithms, how to retrieve data, how to process the data even. And for this, you want to use the most up-to-date sensors you have, or the more state-of-the-art sensors you have, to test your algorithms on. And here we wanted to create a unique data set where you can also see effects of up and down scaling. And on top of this all, we wanted to have an uncertainty added to this, so you know how well you can trust your data and how intercomparable it is. Furthermore, this is also showing how you can go about harmonization of 2 different data sets. This is also important because not only CHIME is being launched at the end of this decade, there is also SPG coming up. And there are quite some efforts between ESA and NASA to harmonize those sensors as much as possible, not make them equal or similar, because then you wouldn't do science. So everyone goes down his path, but wherever you find agreement, you try to harmonize the processings. And adding uncertainty on these 2 measurements allow you to judge if you can compare the data sets or not. So here is the AROSIX reprojection, just very briefly to show you how this, or what kind of effects you had on this and how this was working. We were trying to reproject those images. Here on the left, that's a DESIS image, and here on the right, you see the shift vectors, how the pixels were moved to then line up to the same reference system. Then uncertainty propagation. Let's just jump right into the big fun and let this one here run. So what we did is, besides propagating uncertainties of, in this example here now, DESIS, we also thought of what happens if you are taking a measurement on the ground and you take a GPS coordinate with it. There you also have like an uncertainty. How do we characterize this? And the idea we had was, we take the point spread function. That's the way how a sensor sees a pixel, right? It's not just a square. It also takes into this pixel measurements or effects from the surroundings. This can be described with a Gaussian curve, as you can see here, this Gaussian surface. And the uncertainty was estimated by taking this PSF, how it's called, and let it move plus minus 1 pixel across track and along track, and do this in this area of plus minus 1 pixel randomly with a Monte Carlo sampler. Then you let this PSF run, you decompose your spectrum and collect this, run this like 10,000 times. And then you see down here at the bottom on the left how those spectra are being collected. And then you can summarize them statistically and add them as uncertainty linked to geolocation. And this has an influence on the entire uncertainty propagation, because what we see here is this one in the blue square. This is our measurement function of the comparison between our space-based or airborne sensor with the ground measurement with the ASD. SD is the spectral difference, where we have here our X, this is our space-based sensor, and here our FS, this is our field spectrometer. So we subtract those two, or the spectral ratio, where we divide those two. And here you can see how we go about propagating uncertainties, measurement function in the center box. And then you have those little arms going out, the brown one, the green one, purple one, trying to show where the uncertainties come from and how they flow into this measurement function, also making it traceable to see where it comes from. How we went about this is we used the work of Andy Hüni et al. For the field spectrometers down here. So this is traceable with another uncertainty tree diagram. Andy already did and propagated the uncertainty. And then we have the brown ones. Here are space-based or airborne sensors. For AVIRIS NG, we had to rely on the first uncertainty estimation approach of JPL. For PRISMA, we used a little bit of a trick because PRISMA does not have a fully propagated uncertainty. So what we did is we took in another different mission a 2x2 window of sand, of bare sand, because that is the closest you get to a Lambertian reflection, and compared it to a ground measurement and tried to estimate with the difference between those two measurements how big the uncertainty is, and added this on top of the measurement. For DESIS, what we did is we took the uncertainty of PACO, as we call it. Here, the trick we applied is we took the requirements of PACO and added those as upper and lower boundary to the measurement. So these two flow in here, and then you can propagate them analytically. The results of this we can see here. We have 3 plots. On the very left, we have results for AVIRIS NG. In the middle, DESIS. On the very right, we have PRISMA. Here in this, focusing on the AVIRIS plot, we have here a small plot of the image where we are about. At the very center here in the dark bare field, we have our field spectrometer measurement, the position of it. On the left of it, we have the 2 measurements of those 2 sensors. In red, we have AVIRIS NG. In blue, we have the field spectrometer measurement, the ASD measurement, with uncertainty buffers. What we can see here is AVIRIS NG has very teeny tiny small uncertainty buffers, where I doubt it is like that, but I have to live with it because that's the best approximation we have. With AVIRIS and with the ASD, excuse me, we see the uncertainty buffer is a bit bigger because we added this geolocation uncertainty I showed before. Here on the bottom left, we have the spectral ratio, which is expected to be close to 1. What we can see here, there are some minor differences. Here, especially UV blue, we have a negative ratio. No, not negative, sorry, a ratio close to 0. This is because the spectralon has some effects in the UV blue, which are also described by another work Andy already did, so nothing really exciting here. And what we can see on the right is the spectral difference, which is close to 0. also what we expect. So quite happy with those results. What means that you can compare the ground measurement with the airborne measurement. If you go to a space-based scale, the ground sampling distance becomes bigger. And you can see here with DESIS, you have quite some differences. Also with PRISMA, what you also see in the spectral ratio and spectral difference. Another measurement we did to describe the agreement between those two sensors was the measurement agreement. Here is the equation how we did it. This one does compare the two measurements, including the uncertainty, and there we saw quite an interesting effect. If you add the uncertainty linked to geolocation, you see here in black what happens. You fall within agreement, at least. Sometimes even the data seems to be consistent. If you do not include this uncertainty linked to geolocation, that's the blue curve here, you don't really fall into agreement. This has to do with the fact that we are blowing up the uncertainty envelopes, and you are consistent or in agreement if those two uncertainty buffers overlap of the two measurements. Here you see three different plots because we did it at different confidence levels, or also K levels. K equal 1 is the smallest one. That's why you only have small bits and pieces of the spectrum being really consistent or being in agreement. Then what we did on top of this is we resampled AVIRIS NG to a 30-meter ground sampling distance to be able to create this multi-scale data set, also to do a better intercomparison between the three different sensors. Here you see how those images should be lying on top of each other. In green, you have DESIS. On red, you have the extent of the image of PRISMA. And in purple, you see AVIRIS NG. And this is what it looked like in the end. So not really nice squares because the image within the file is a bit tilted. Here you have in yellow DESIS, in purple PRISMA, and this grayish looking one is AVIRIS NG. And you see with the rubber sheeting approach we used, they really nicely align. And this is the last thing we did. We also computed a reference sensor. This was computed with a weighted mean of the three sensors, AVIRIS NG, PRISMA, and DESIS, where the weights were computed with the inverse of the uncertainty. This means the smaller the uncertainty is, the bigger the weight, and vice versa. And here is a little example how this situation looks in this multi-scale data set. You have in light blue here, or in turquoise, DESIS, in green, AVIRIS NG, in blue you have PRISMA, and in purple you have the reference sensor, which is obviously following more the shape of AVIRIS NG because it has the smallest uncertainties. The differences we found, especially between DESIS and AVIRIS NG, are due to the recording time. PRISMA was recorded at about 9:30 UTC, what is quite early in the morning where you have very low sun angles, whilst AVIRIS NG was flying at really local noon with the highest sun angles. So this means we have some BRDF issues which are currently being estimated by our colleagues at University of Valencia. With this, I hope I gave you a little introduction on how to do uncertainty propagation, and I thank you for your attention and happy for questions.